morning, guys. Welcome to the second class of marine corrosion. And today we are going to talk about metal alloys, ferrous alloys, non-ferrous alloys. And I want that you memorize some specific marine alloys that you should use in the future. And don't forget, in the future, because you study a lot in this program, you need to be with the other contractor. Hey, my friend, this is not marine grade. This is not a marine alloy. This is not a metallic alloy. Those screws are Mickey Mouse screws. Those washers are Home Depot washers. This is not allowed in my design, in my boat. Okay, guys? Why the alloys are important? If you have the metals by itself with great properties, why you need alloys?
Because they don't possess all the properties or certain properties?
Yeah, because you need reinforce some properties.
Strength, non-corrosion.
Right, the corrosion.
You need inhibit the corrosion, or eliminate the magnetic properties, or improve the hardness, or improve the malleability. When you alloy, exactly like when you prepare the soup. Oh, the soup of beef, the soup of chicken. And if I added celery, oh, that will be nice because this and this. Oh, if you added pepper, no, this is an alloy. It's a soup. Those are the alloys. But prepare an alloy is another career. The metallurgical engineers specialize in those alloys, no? Can you imagine the amount of metallurgical engineers in Chrysler, in General Motors, in Ford, in NASA, in Boeing?
Oh, maybe not Boeing.
No, but can you imagine the salaries of those metallurgical engineers? Yeah, I know. Of those metallurgical engineers in those companies? Those guys change the life of the people. For example, the guys that discovered that magic alloy in aluminum, duraluminum. The aviation is divided in two: before the discovery of duraluminum and after that. That alloy changed the aviation dramatically. That alloy have properties, incredible properties. In some properties have more ability than steel. Duraluminum is, later we are going to talk about that. The same with marine alloys. The marine alloys have a lot of work. Engineers working years and years and years, finally to discover the nibral. You remember? The alloy for the propellers. Or to discover the monel, the alloy for the shaft. Or to discover hundreds of marine grade alloys. It's a lot of money, no? The majority of those alloys are coming from the engineer department in the military. This is why the majority of those alloys, originally, the formula is MIL, military, Those formulas are nice, no? Okay, guys. And today we are going to study two types of alloys: ferrous alloys and non-ferrous alloys. And we are going to check what happened with ferrous alloys, what happened with non-ferrous alloys, what type of ferrous alloys are not good for the marine environment, what type of ferrous alloys could be excellent in marine scenarios. Okay, this is why I want to study a little, no with a lot of details, the iron and the ferrous alloys. What is the meaning of steel, stainless steel, low carbon steel? We are going to talk about that quickly in the presentation that you have in your book. Let me check quickly. Look at this. The ferrous alloys are classified according with the addition of one component. What is the component that improve the properties of the ferrous alloys or damage? Carbon. Once again, carbon. And it's not too much carbon. Carbon between 0% and 4%. 4% is nothing. Depending how much is the composition of carbon in that alloy, you have cast iron, you have steel, middle steel, low carbon steel, ultra low carbon steel, and depending of that composition of carbon in the entire alloy, you have special steels. No? Different steels. The people think that steel is only stainless steel. No, stainless steel is one type of steel. No, there are special steels for different industries. No, for oil industries, for automotive industry, for agricultural alloys, naval alloys, aviation alloys. All right, guys, look at this. The ferrous alloys are organized in cast irons, plain carbon steel, and special alloy steel alloys. Okay. The worst ferrous alloys are the alloys with high content of carbon. High content is considered between 2% and 4%, the maximum. Between 2% and 4% of carbon, you have cast iron. Cast iron. Cast iron is cheap, is brittle, you can fracture easily, is practically impossible to weld cast iron because the amount of carbon, you learn with your professor, weld cast iron is impossible. You remember one typical example of cast iron is the exhaust manifold. This is cast iron. If this exhaust manifold is cracked, you can weld it? No. You can weld and lose like but in 2 days, it's broken again. No? Okay, I know professional welder with excellent equipment, and the result looks perfect, but in 2 months it's broken again. Because this material have too much carbon. If I drop this element on the ground, it's fractured. It's cheap. It's cheap. What is the most abundant metal on the environment? Iron. Iron is too cheap. It's the most abundant, but it's also the most strong. This is why it's used. All the structures on the buildings are based on iron. Iron with carbon, no? Steel. Yeah. More than 2% of carbon is considered cast iron. Cast iron is cheap. It's not good. For example, the drums for the brakes, yeah, those rotors are in cast iron. Cast iron is highly corrosive. In that organization of cast iron, you have different names: gray irons, malleable, ductile, graphite iron, ductile, white. All of them are cast irons. Some of them, they have the iron organized in some form, in other form, but it's cast iron. Let me explain what happened with carbon. You remember that I explained at the beginning of the class that carbon is magic, no? In some cases it's lubricant, in some cases it's used to fabricate the cutting tools, no? The blades with diamond, covered with diamond.
With diamond dust.
Correct. Drill bits with diamond. In some situations, it's the hardest material on the world. In some situations, is lubricant. No? The pieces of carbon in that alloy, in cast iron, the carbon is aggruppated in like small rocks. If you cut this element and you polish and you check in the microscope, you see the pieces of carbon. You see the pieces of carbon organized in some parts. The problem with those sections of carbon is that around those sections the cracks are propagated because the bubbles are produced in the neighbor of the carbon. If I cut one piece of this cast iron and I polish, I see the structure, the atoms of iron, and the pieces of carbon, and around the pieces of carbon, bubbles. In the corners, bubbles. What happened with those bubbles? For example, in this equipment. This equipment is working at a high speed, rotational speed. And this is cast iron. And for sure, in this cast iron, there are small bubbles. What happened with the bubbles?
Different densities, so some
Propagate and produce cracks. When the temperature, the difference in temperature occur. Normally, in normal condition, what is the temperature of this rotor when the caliper is working?
Very high, pretty high. Yeah.
And what happened when I enter in a section with water,
Cools down a little
splash
bit.
water, and what happened with this? That contrast of a temperature produce, accelerate the cracks, and that's the problem. You understand? The organization of the pieces of carbon. That's the problem. Look at this. Less than 2% star steels, and less than 1% low carbon steels.
Yeah, I think it's like 0.3
Okay,
or something.
those are
Yeah.
plain carbon steels, high, medium, and low carbon. And special alloys. There are alloys with low level of carbon and other ingredients like a silica, a nickel, chromium, and those are the low carbon steel or special alloy of steel. Cast iron content is between 2 and 4%. Carbon steels are classified by the percentage of carbon in hundreds. Low carbon steels, pay attention, low carbon steels is considered the content of 0.3%. Medium carbon steel between 0.3 and 0.5%. And high carbon steel between 0.5 and 1%. Okay, this is high carbon steel. Around 1% is high content of carbon. 1% is practically nothing. But that amount change dramatically the condition. Those are considered low, medium, and high carbon steel. And stainless steel, the carbon content is around 0.08%, less than 1%. Stainless steel, the content of carbon is too low. It's less than 1%. Don't forget that. Okay, cast iron. Oh no, cast iron is, look at this. The content of carbon between 3.5% and 4%, a lot. And other ingredients, manganese, phosphorus, sulfur, and silica. Oh yeah, my friend. Look at the other alloys, the other ingredients. Phosphorus and sulfur. Phosphorus and sulfur are bad ingredients. Cast iron in general, by itself is not good. And the other friends of him is like a bad guy, no?
We cook on that.
This is a bad guy. And the friends of him, oh, worse than him. No? Exactly like a cast iron. But in cast iron, you fabricate, look, the majority of the block of the engines are in cast iron. You remember in the diesel class, the sleeve, we remove the sleeves on the cylinder. You remember? On the block. The sleeves is in a special low carbon steel. Low carbon with vanadium, titanium, and other ingredients. However, the block is cast iron. The block of the engine is exposed to high pressures. The block. No.
No, not pressure.
No.
Temperature.
No. The liner, the cylinder, yes. You remember? We remove the liners, and those liners are special material. But the block now. The block is cast iron. And look at the structure. Look at this. What is this? The black ones.
It's carbon.
The carbon, the concentration of carbon. Ah, look at this. In a gray cast iron, this is the concentration of carbon with those corners. That's not good. But look at this. This is ductile cast iron. And the concentration of carbon is like a circle. That's good. That's better. You can improve that one if you added other ingredients, magnesium, they help to round it, the structure of the carbon, and that will be better. This is why there are different type of cast iron. Good cast iron, medium, and not good. Okay, the block is in gray cast iron. It's not perfect. Gray cast iron, excellent for vibration, for brakes, drums, rotors, clutch components. It's good in compression, engine blocks, cylinder liners, heads. The machinability. What is the meaning of machinability?
It can be cut with a
Yeah, you
bang,
can work
say.
with the lathe. You can, yeah, it's good. The heat transfer is excellent, and it's cheap. It's too cheap. The gray cast iron. Gray cast iron in different applications. Rotors for brakes, drums for brakes, manifold for exhaust, blocks of engines. All right, why cast iron? Why cast iron is better? You see the concentration of carbon is like a small circle. Why cast iron has superior tensile strength, better malleability, is malleable, and the graphite is spherical. That's better. Why is better spherical and no longer?
Really great crack.
Because the propagation of cracks. With the spherical, practically nothing. Why cast iron have a carbide? Those concentration of carbon, the name of those concentration is carbides. Carbides impurities which allow cracks to pass straight. Carbide, Yes, those are the concentration of carbon. How can I eliminate those concentration of carbon in a cast iron alloy? Can I convert the cast iron in a good steel? No. You need once again melted the material and try to eliminate in the foundry the carbon. This is a long process. In the course of metallurgy, I explained that process, but this is not part of this program. Okay. Why cast iron? You remember that the turbo on the diesel engines and gasoline, the turbo is divided in the hot section and the cold section. The cold section is the compression of fresh air, and the hot is where the gases enter, spin the turbine, and goes out. No, that hot section is in cast iron. It's cheap, cast iron. And why if I have areas with too much heat transfer, I use it cast iron, because cast iron have excellent ability to dissipate the heat faster. No, other alloys they retain the temperature for long period of time, but the cast iron reach high temperature and release the temperature quickly. This is the advantage of cast iron. This is why the manifold of the exhaust, the risers, the rotors are in cast iron, because of course they absorb a lot of heat but release the heat quickly.